So we are back in our probability. All right, let's see. Okay, let's start off here. We're going to look at tree diagrams to help us with probabilities and counting, which helps us with probabilities. Okay, so there's a store. They have jackets in two colors, black and red, and they have 4 sizes: small, medium, large, and extra large. So we can use a tree diagram to help us organize all the possible size and color combinations that result in a different jacket. How many different types of jackets would you have? So what we do typically is we'll set up one or the other. In this case, I did size first. I have 4 sizes. Okay, 4 sizes up here. And down here for colors, I have 2 colors to choose from, black or red. So 4 sizes, 2 colors. Okay, so we have 4. And what I did was I branched off. For small, you can have a red or a black. For medium, red, black. Large, you can have red or black. Extra large, red or black. So with 4 different sizes and 2 colors each, we have a total of 8 different combinations of size and color for these jackets. 8 types in all. And you can list them as I did here on the bottom. Notice I just took the branch here and got small red, and I had small black, and the next one is medium red. So you just trace along the branches and you can make up the combinations. And there are 8 of them for this one. Okay. Now, let's look at the next one. Okay, back to this problem. If you select one of these jackets at random, what's the probability that it's a large black jacket? Well, you can look at your, this is your sample space right here, the way I've drawn it. That's your sample space. You can put commas in here. And you can put the whole thing in a set. It's your set of possible outcomes here. And each one has the same likelihood of being selected. There are 8 of them. Each one has a probability of 1/8 of being selected. We're assuming the jackets are all mixed up in a box or something, a big box, and you just pull one out randomly and you select it. And it has 1/8 of a chance of being selected. So each type. So a large black would be L with a B, and there's only one of those in the whole list, so it's 1 out of 8. Okay, so probability of the LB, let's say that probability of LB is 1/8. Okay, so that's how you can use that tree to construct a sample space. And that gets you to be able to answer those questions about your probabilities. Okay, so let's go down. Small windbreaker, that's probability of a small red. So it says small. Okay, it's small red or small black. Okay, so if either one of those turns up, we have a so-called success. So here, notice I have 2 out of 8 that fit that description. So small red is 2 out of 8, which is 1/4. A red windbreaker. Okay, now look at your list and you'll see how many reds are possible in here. Okay, I see 1, 2, 3, 4 out of 8. So your probability would be probability of a red equals 4 out of 8 or 1/2. Okay. Now I use something up on top here, which is better known as the counting principle. And that is, if one operation can be done m ways, and a second operation to be followed can be done in n ways, then if you put them together, you can do the 2 operations in succession. First one or the second one doesn't matter, but you can do it in m times n different ways. So we can use this to count the number of items in a sample space. And that'll help us with probability. So we did that up here, this one, and that's where I got that 8 here. Okay. Now, let's look at this next problem. Okay, a small business has 4 employees. 2 are going to be selected randomly to go on a business trip. Okay, so how many different ways can these 4 people be selected? From these 4 people, how many different ways can we select 2 at a time? How many different ways? Now, we're going to consider, let's say we had 4 persons. We have Gene, Bill, Carol, and Harry. We'll consider Gene being selected first, Bill second is different from Bill being selected first and then Gene. So I built a tree here. Now, first of all, before I even do that, I know how many points will be on this tree, what this tree will amount to. Because I have, for the first person selected, there are 4 people that could go in that first position. Okay. Once one of them selected, you still have 3 left for the second ticket. So this is the second ticket or second person chosen. So 4 times 3 is 12. So we have 12 different ways that people can win these tickets, so to speak. We'll assume they want to go to Hawaii. That's kind of a prize. So to construct a tree, you can start with person 1, person 2, list all the possibilities for person 1. Here they are. And then from person 2, you have the remaining 3 people as possibles. So Gene first leaves Bill, Carol, and Harry to be picked for the second choice. So these are the first choices. Here are the second possibles. So if Bill gets picked first, then that leaves Gene, Carol, and Harry possibly pick second. Carol, Gene, Bill, Harry. Harry first, Gene, Bill, Carol second. So a number of ways the first person can be chosen is the 4 that's in here. And the number of ways the second person can be chosen is a 3. So we know we're going to have 4 times 3. Now, if you want to put all these, get these together, you have Gene, Bill, Gene, Carol, Gene, Harry on the first set here. And then you have Bill, Gene, Bill, Carol, Bill, Harry. Then you have Carol, Gene, Carol, Gene, Carol, Bill, and Carol, Harry. And then finally in the last group down here, you have Harry with Gene, Harry with Bill, and Harry with Carol. So this is your sample space here. There are 12 different points in this sample space. We call each one of these a point. Okay, so this is your sample space. Put it in like this, sample space. So the tree helps us to decide what the sample space is. You don't need the tree necessarily if you can organize your thought, but the tree helps you organize your thought. So let's see the next question now. Use the sample space to answer these questions. What's the probability that both Jean and Harry are selected for the trip? Jean and Harry. All right, go to your sample space and pick out if you see Jean and Harry. Okay, I see Jean and Harry here. Here's Jean and Harry over here. So that amounts to 2 out of the 12. Oops. 2 out of the 12, which is 1 out of 6. Okay, what's the probability that neither Bill nor Carol is selected? Okay, well, let's go back over here. And I'm going to use a different color here. I'll go with blue. So I want neither Bill nor Carol. So I have to come through here and look for something that does not have a B or a C. Okay, here's one. Here's one. That's it. Turns out that's the same question as asking that we asked for the first one. Okay, so in any case, we have a 2 out of 12, which is, again, 1 out of 6. Okay, the next one, what's the probability that at least Bill or Harry gets selected? So now we want to look for anything that has a B or a Carol. Probability that Bill or Carol is selected, B or C. So I'm going to use another color now. Let's go with red. Okay, so I'm looking for a B or a C. Here's one, here's one, here's one, here's one, here's one. Notice that one has both. Okay, B and C. Here's another one. Oh, here's another one that has both. That's interesting. And another one, another one, another one. Okay, if you look at all the red ones that I just circled, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got 10 out of 12. That's 5 over 6. Okay. All right, let's continue. Okay, next page here, we see okay, we're going to look at, in this case, or and probabilities of problems. Now, we know these to be called compound probabilities. And the first thing is to look at we're going to start with a formula here. Okay, and think about why this formula might be true. We can reference that last problem that we did. We're going to reference that in example 1. We didn't use this idea to compute the probability, but we could. You can imagine it's possible your sample space is really large and maybe you don't have it in front of you. You might have to resort to a formula like this. It might be more convenient. So it's good to have it available. Now, Bill or Carol, probability of Bill or Carol, turns out that it's the probability of Bill plus Carol plus probability of Carol minus Bill and Carol. Why is that? Why do we need to subtract that off? Well, it's because when you calculate probability of Bill, you will inevitably, if it's possible, that you'll be counting in pairs. You might be counting Bill and Carol. So then when you go to calculate probability of getting a Carol, you might also count a Carol with a Bill, which you already counted if you calculated probability of Bill. So in other words, if you look back at that sample space in here, when you calculate probability of Bill and Bill or Carol, you look for all the B's first, and you notice we have 1, 2, 3, 4, 5, 6. So you have probability of Bill 6 out of 12. Okay. So if we just say, well, I'm just going to add probability of Carol and count those 1, 2, 3, 4, 5, 6. 6 of those. Okay. Now, if you added these, you'd have a 1. But you know that's not possible because there are other things that might have happened. I mean, if it's 1, that means for sure it's going to be Bill or Carol. What about Gene and Harry? Where do they come in? They're not there. You know, it's impossible that it's not possible that this is a sure thing that Bill and Carol can one or the other get picked. It is still possible that Harry and Gene get picked. Okay. In fact, you can see there are 2 ways that can happen. So the point is here that why do we need to subtract that Bill and Carol? We got to subtract that. Oops. B and Carol. You know, I'll just put on like A here for and. Bill and Carol. That happened here. And happened here. The reason we counted those twice, basically. Okay, I counted the Bill and Carol here once when I was counting just the bills, and then I also counted this one. Okay, because it had a B, so I counted these 2. I counted them twice. I counted once a piece for the bill, and I counted them again, both of them again when I was counting the Carol instances. So the point is, I'm counting them twice. I have to subtract off 1 of each of those. So that amounts to 2 of them. 2 out of 12. Okay, so now I end up with 10 out of 12. And that's going to be my probability. 10 out of 12. Okay, so that was one way to justify the formula. Was it the best way to do the problem or the only way to do the problem? Answer the question, no, it was not. But that kind of justifies our formula. And so this is why we're doing it the way we are here. And we end up with that 5/6. Okay, now let's talk about and probabilities. This is our definition for a probability. We're looking at 2 things happening in succession, both of them happening at the same time, in a sense. So our question in this case, a good example would be this number 2. How is this illustrated? You pick 2 cards from a deck, standard deck, without replacement. Okay, so it stands to reason that the probability of the second card, whatever it is, okay, in this case, we're wondering about the probability if we get 2 aces in a row. So the probability of the second card is affected by what happens on the first draw. Because number 1, there'll be less cards to pick from. 1 card was removed. And number 2, if we assume that card was, in this case, an ace, then there'll be less aces in the deck to pick from. So now when we do this, the standard idea is to assume that one was, in this case, a success, was an ace, and it happened on the first draw. So that theoretically then, because this is theoretically then we have 1 less ace in the deck to pick from. So it's a theoretical probability. So we can assume in theory that the ace was drawn on the first pull. Okay, so we have to assume that, otherwise our next probability we wouldn't have any theory to base it on. So here's how we do it. The first ace is 4 out of 52. assuming that there was an ace drawn, then they have 3 aces left and only 51 cards because one is missing, the ace. So the definition of the AND probability is that we multiply these when we have this situation. So if you want both of these to happen together, you have to multiply the two probabilities to calculate the theoretical probability that they will happen, one and then the other right afterwards. So then you just reduce this fraction, you get this number. So from now on, when you see that word and, okay, and you would be thinking about multiply. Okay, and when you see the word or, you're gonna be doing some adding. Okay, so and, multiply, or add. That's the difference. Okay, so we'll try to remember that as we go through. That's really the most important part of that. Ors are adding, and ands are multiplying. Okay, so here's a few more problems. 2 cards chosen from deck at random with replacement. Find the probability that both cards selected are aces. Okay. Ace followed by ace. So ace on the first draw is 4 out of 52. All right. If the cards are put back in, then nothing's changed. It's still 4 out of 52 for that second draw, and we multiply them together. So this is 1 out of 13 times 1 out of 13, 1 out of 169. Okay. So you see the difference between replacement and non-replacement. Okay, there it is. All right, an urn has 10 blue balls and 8 red balls, 2 balls selected at random from the urn without replacement. What's the probability that both selected balls are blue? Well, notice without replacement. Pay attention to those phrases. Without replacement. So we want a blue ball, which is 10. That probability is 10 out of 18. Then we're going to multiply that by another. We want another blue ball, so there must only be 9 left out of 17. So let's see, that would give us a 9, the 2, and that goes in 5, so we get 5 over 17. Okay, what's the probability that the first ball is red while the second ball turns out to be blue? Okay, first ball red, 8 out of 18. Second ball blue, well, we still have 10 of those, but only 17 total. Okay, so this one now, let's see, we got a 5 and a 9. So we got 40 over 90, 63 is 153. Okay, what's the probability that at least one of the balls selected is red? Okay, so this one's a little tricky, but I want to show you a shortcut. At least one, whenever you see that phrase, at least one, then we're talking about complements here. We can use complements, possibly. We can use complements to help us. At least one. Okay, there are really, when you think about it, let's look in the margin here. You're selecting these 2 balls. Now, the only things that can happen are you have a blue with a red, possibly a red with a blue. You might have 2 reds, or you might have 2 blues. So those are the only things that can happen. Now over here, he's asking for at least one of the balls selected red. Well, at least one means this thing, that counts, this would count, and so would this. So notice there's only one other thing, one other outcome that can occur here, and that would be 2 blues. So when you look at this, this is at least one red. It is the complement of this one, which is 2 blues. So if we can figure out I mean, of course, we could calculate the probability of this right here. We can get that directly if we're careful. We can calculate it. But it seems easier to just figure out two blues. Okay. Seems easier to just figure out two blues. The fact is, we already did that work. We did it up here. And you see how easy it was, 5 over 17. So the point is, whatever this is, whatever this probability is, let's just call it x. When you add it to this probability, which is 5 over 17, you'll get a 1 because they're complements. So our probability that we need right here, let's call this P for probability. That probability is just 1 minus 5 over 17, which is 12 over 17. So probability at least one red, okay, in other words, 1 or 2 reds, right, is 12 out of 17. And that's the fast way to do it. The other way, it would take more time. You'd have to compute each one of these probabilities separately. Probability of a blue followed by a red, okay. Then, see, this is this or this, right, or this. So you'd be calculating this probability, then add it to this one, then add it to this one. Now, there's no way that these events can occur at the same time. In other words, you can't have an and. You can't have blue and red and blue. That's not possible on the same draw. So you don't have to worry about subtracting any ands probabilities in this case. Just figure out those separately. Probability of the blue and red, and then the red and blue, and then the red and red together like that, in that order. And you should still get the same number, 12 out of 17. So I can show that how you can get that if you don't believe me. You'd be taking blue and red, which would be blue on the first one. We did that already. I think we did it. First ball, second is red, second ball is blue. So that's our second one here, but it's the same as the first one. So we'd have 40 over 153. That's the second probability. That's this one. The first one, blue with red, is just, it's going to be the same thing. It's going to be 10 over the 18 times red, which is 8 over 17. But notice that was the same as this computation here. It's the same thing. It's a 40 over 153. So you're going to add those together. And then we still want to add 2 reds. Okay, 2 reds would be, probability of a red was 8. So you have 8 over 18, and then 7 over 17. So that comes out to be, let's see, 28 over 153. And that equals 80, 108 over 153, which is, whoa, okay, went a little too far there, which is 9 times 12. Whoa, gotta be careful there, over 9 times 17. Yeah. And there's our 12 over 17. Okay, same as the 12 17s we got here. Which way was easier? I believe using the complements was. Okay, and you'll have to trust me on that because we're going to see that happen again to us. Okay, so let's continue. All right, here we have some problems with some spinners. Okay, spinners spun twice. Find the probability that the pointer lands on red and then yellow. Okay, so red would be a half times yellow would be a half, 1/4. Okay, spinner spun twice. See, now notice here, there's no replacement. This is like a problem with no replacement because we all know how spinner works. You spin red, and you spin again, and again, and you're not changing anything. Every probability remains the same after each spin. Now I'm picking those balls out of the urn and without replacement. Okay, so the pointer lands on, okay, spinner spun twice. Find probability the pointer lands on red both spins. Okay, how many reds do we have here? Assume each one occurs with the same likelihood, so 1/6 probability for each of these colors. We have 2 reds, so that's 2 out of 6 on the first spin, and then a 2 out of 6 on the second spin. Well, that's reduces to what, 4 out of 36, which is 1/9, right? It's probability the pointer does not land on red for either spin. Okay, no red means greens and yellows. Well, there's 4 out of 6 ways for that to happen. On the first spin, times 4 out of 6 on the second, which makes 16 out of 36, which is 4 out of 9. Okay. Okay, a couple has 3 children. Find the probability that all 3 are boys. Well, one birth does not affect another. Has nothing to do with it. So probability of a boy on the first child is a half. Probability of a boy on the second child is a half. Third child is a half. So this is an and situation. Boy on the first and the second and the third. So there's the word and. All 3 are boys. So we end up with a 1/8. Okay, what's probably the youngest child is a girl and the other children are boys? Well, okay, so that's, we want boy, 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 girl in that order. Okay, so we'll say this is the youngest. This is old to young. So probability of a boy on the first child is a half. A boy on the second is a half, and a girl on the last one is also a half. So that's also 1/8. Okay. Now, you could also, for a problem like this, I mean, you don't have to, but just for small sample spaces, you can build a tree. You know that, let's do it like this. Let's do first, second, and third. So for the first child, it could be a boy or a girl. Let's do it like this. Second child can be a boy or a girl in this case, and over here it could be a boy or a girl. And the next child over here could be a boy or a girl. This one could be a boy or a girl. This one could be a boy or a girl. And then finally this one, boy or girl, boy or girl. So let's look at all of these choices here. The choices are coming down. This is how we build our sample space. Coming down each branch like that. There's the first branch. And I list what I have there. Oops. Okay, I list what I have over here. I have boy, boy, boy. Then my next list coming down this way, I have boy, boy, girl. And I continue and come down this way. I have boy, girl, boy. So this is how you can build your sample space from the tree diagram. So I continue, boy, girl, 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 boy, boy, girl, oops, girl, boy, girl. And let's do another one over here. Whoops. My ink is stuck on. Okay. was turned on like that. Let me clear that up. That's kind of weird. Okay, so let's see. I had the girl, boy, girl. That was girl, boy, girl. Now I got girl, girl, boy, and then girl, girl, girl. The last one. So count them up. 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. There's that 8 what we saw down there. See the 8 that came up? Now, which one of these has boy, boy, girl? Well, let's find it. Here it is right here. There are no others. That's boy, boy, girl. It's 1 out of 8. Okay. So which way is easier? Well, in some problems, these sample spaces are nice to have. In other problems, you don't really need them. So the tree is a tool. Sometimes you'll use it, sometimes you won't. Okay, won't need to. All right, we've got one more problem here. Okay, each question on a 5-question multiple choice exam has 4 possible answers. Randolph guesses the answer for each. What's the probability he selects the correct answer on a question in general? So we don't know. It says 5 questions to it, but we're just asking a question in general here. So any question. So each one has 4 possible answers. Okay, each question. So I'm assuming there's only one right answer. So he has a 1/4 chance of getting a right answer on any given question. Okay. Now, so that's a question in general. Okay. It's probability that one question in general, any question. Okay, so now what about the probability that he gets, second part, only the first question correct? Okay, only the first question. That means he wants to get the first one right, only the first question. So it'll have to be, let's see, it'll have to be, let's see. Okay, here we're back again. Now, okay, only on the first question. So here's how it works. This is the first question. There's a probability that that first question is correct is 1/4. And he wants to get the next 4 questions wrong. Because he's asking, what is the probability that he only gets the first one right? That means he has to get the other 4 problems wrong. So he has a 1/4 chance of getting the first one right, 3/4 getting the next one wrong, next one, so on. So we would have, what is that, 81 over, what is that, 16, oh gosh, 16, 196 times 4 is what, 256, I believe. Okay, 256. Okay, now this one says exactly any one of the 5. Exactly any one. Okay, any one of the 5. So that means he might have the first question right, the next 4 wrong. Or he could have first question wrong, the next one right, and then the next 3 wrong. Or he could have the first 2 wrong, the next one right, and then the last 2 wrong. So each one of those probabilities is the same. It's actually the same as part B that we did. In other words, it doesn't really matter where you place that correct question. If it's in the middle position, the third question, or the last question, we're just mixing up these same numbers, 1/4 and 3/4, just mixing them in a different order. The number won't change. The 81 over 56 won't change. So exactly any one of the 5 questions. So any one. So in other words, first question right, and the next 4 wrong, or first question wrong, the next question right, and the next 3 questions wrong, and so on. So we basically have 5 ways to do that. 5 times this 81 over 256. Those are 5 ways that can happen. Okay. So again, that one. Let's see. This one, or this one, or this one. Let's see. Okay, so this number coming here. Now this is what, 405 over 256. Okay, now what's wrong with this? You should be asking yourself, is this possible? Can a probability be bigger than 1? No. And yet this number is. So something isn't right here. Let's go back. Let's look at this number here. This logic on this one seems okay, which is what I'm basing my answer here on. But I'm going to double check my numbers there. Let's see, that 4. Okay. Here's the issue. It's this 256 in here. It's not 256. It's 1024. And you have to pardon me on that. That's my mistake. Okay. I just realized I had 4. I only had that as 4 to the 4th power, and it should have been 4 to the 5th power. So it's 81 over 1024. That makes this, that's this 1024, and makes this 1024. So our answer on this second problem is 405 over 1024, which, although you might say no guarantee that's correct, at least it's not blatantly wrong. Okay, in other words, it's a number less than 1, which is what we expect. Probabilities will be between 0 and 1, sometimes 0, sometimes 1. Okay, so that led us to, it was actually a good thing to talk about there, having that mistake on my part. Okay, let's look at this next one. See here, only the 3rd and 4th questions correct. Okay, only the 3rd and 4th questions. So, third question, here's the 3rd and 4th right in here. They have to be correct, so there's a 1/4 probability that they will be. The other 2 questions in front, 1st and 2nd, and then the 5th question have to be wrong. Those probabilities are in place. Here's your product, and there's your final answer. Okay, what are probability that all 5 questions are correct? Well, you have to be 1/4, 1/4, 1/4, 1/4, 1/4. There's only one way that can happen if they're all correct, and that would be 1 over 1024. Not likely that that's going to happen, especially if this is assumed guessing, right? So that would be pretty unlucky person to get all of those correct, just on complete guessing. Okay, none of the 5 questions correct. Well, that's sort of the flip side of that coin. 3/4, 3/4. There's only one way that can happen, just like that. And that's going to be 1024. And what is that? 81/3 is 243. Okay, so there's a better chance that that's going to happen when they guess. That things are not going to go right for them. 243 out of 1024. And even that's not a sure thing. It's pretty likely that they're going to get something right, even from guessing, unless they're really unlucky. Okay, but that could happen. So 243 out of 1024 chance that they'll get all 5 questions wrong by guessing. So, all right, next question, last one here. Let's see. Okay, here it says at least one of the 5 questions correct. Ah, there's that at least one question again. At least one. So we know at least one, the complement of at least one is what? Complement of at least one is none. None correct. Okay, so that's our complement of at least one, is none. None means that they got all 5 wrong. Okay, that's an easy probability. At least one is none. So we know this probability of at least one will be equal to 1 minus probability of none, which is, we just did that last one, 243 over 1024. We just did that one. None of the questions. So here, do a little math. Let's see, 1024 minus that 243. We get 781 for 1024. So there it is. It's another use for that complement idea that we talked about before. Now, you could do this the other way, but you are talking about a lot of work. You'd have to look at all the probabilities, all the different ways you could get. It would be a good exercise in thinking, but not very practical. So at least one means 1 right, 4 wrong. Okay, so 1 correct, 4 incorrect. Okay. That's at least 1. Okay, or you can have 2 correct, 3 wrong, incorrect. You can have 3 correct, 2 incorrect. You can have 4 correct, 1 incorrect. Okay, so all those mean at least 1. And then you can have also 5 correct with 0 incorrect. Now, you'd have to figure out what are the probabilities for each of these happening and then add them all together. They are mutually exclusive. You don't have to worry about any ands in here, but you will have to add them. So 1 correct, 4 incorrect. The trouble is that could mean the first one wrong. The first one right, the next 4 wrong. It could mean the first one wrong, the next one right, the next 3 wrong. It could mean, so you got to calculate all those probabilities for each of those cases. Now they're all going to be the same. You just have to figure out how many ways you're going to do that. So it's not going to be a simple task to figure out these probabilities in here. It's going to take some work. Like I said, 1 correct, 4 incorrect. So there are several ways that can happen. You can have the first one right. Okay, first one correct, and then the next 4 wrong. You could also have a wrong, correct, wrong, correct, wrong, correct, wrong, correct. So whatever this probability is for this first one, we got to multiply it by 5 because there are 5 ways for this to happen. So I think we actually did that probability, the first one. We did that up here, I thought. Only the first question. See, that was 81 over 1024. So you'd have to multiply that. Okay, in other words, these are all the same, so it's 5 times 81 over 1024. Okay, so that's the first one. Now you got to do this one. Okay, now this one, 2 correct, 3 incorrect. So you might have those 2 and then these 3. you might have this one, a wrong one, this one, wrong, wrong. You might have this one, wrong, wrong, C, wrong. You might have this one, this one, this one, C. Then you might have wrong one here, correct one here, wrong, wrong, correct. You might have a wrong one, correct one, or sorry, a wrong one here, another correct, wrong, and a correct. You got to keep track of all this. Wrong, 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 correct, correct. Okay. Are there any more combinations here? Sure, I think we can come up with more. You could have, and so you got to do this systematically. You might also have like the wrong one, wrong one, wrong one. Or sorry, here two correct ones like that in that place. I didn't do that one here. Okay. So did I miss any? I don't know. This is starting to get messy. Point is, you got to calculate all these without any other kind of knowledge of how to do this. This is how you'd have to figure out these probabilities. And then, of course, I believe this one would turn out to be the same because it really is just asking the opposite question. The number of ways you can do this, the probability would be different, but the number of ways that you can arrange these, 3 correct with 2 incorrect, it's going to be the same as this one here if I can get this right. So if you keep going in here, I don't know if I got all these done. Correct, correct, wrong, correct, correct, wrong, wrong. I don't even know what I got here. So the point is, you'd have to keep working on this, and it's a lot of work. We avoided all that over here. Okay, we avoided it. It would be nice to finish this one up, but I don't want to spend all night working on that to make sure that it's correct. So we'll stop it at that point.